In this video, we're going to determine the Ka of an unknown weak acid when we know the initial concentration of the acid and the pH. In our first example, a 0.100 mole per liter solution of an unknown acid is 3.450. What is the Ka of the acid? So we're going to start by writing a generic ICE table, a generic ionization expression. So when we don't know the identity of an acid, it's common to represent it as HA. So our acid HA will react with water. That's going to form A- and hydronium. So we can write ice down the side, and we can fill in what we know. So we know the initial concentration of our acid is 0.100, and we know that we won't have any of our conjugate base or hydronium in our initial solution. We can then fill in our hydronium ion concentration at equilibrium. And we're going to get this from the pH. So, at equilibrium, our hydronium ion concentration, H3O plus, is going to equal 10 to the minus pH. So 10 to the negative 3.450. And we get 3.55 times 10 to the negative 4 moles per liter. So we can fill that in for both of our equilibrium concentrations. And we know that that's therefore the change. So our change for our products is going to be positive 3.55 times 10 to the negative 4 moles per liter. And our change for the reactants will be negative 3.55 times 10 to the negative 4 moles per liter. Now, because this change is so small, our reactant, or our equilibrium concentration of our reactants, is not really going to change by much. So it's going to be 0.0996. So when we make our assumption of less than 5% ionization, this would be a case where we would probably do that because this value is so similar to this value. Because we don't have to, though, we don't have to worry about that assumption and we don't have to round. So our Ka is going to equal our concentration of our conjugate base times hydronium divided by the concentration of our conjugate our acid. We can plug in our values now. So we're going to have 3.55 times 10 to the negative 4 moles per liter on the top. That will be squared, divided by 0.0996 moles per liter on the bottom. And I'm not actually going to round when I put this into my calculator, so I'm going to keep the exact numbers that I'd calculated before. So if you get a slightly different answer, it might just be because you've rounded during the question. So we should get 1.26 times 10 to the negative 6. So we have a pretty middle of the road acid. Definitely less than 5% ionization taking place during this reaction. So if we were going forward to find the pH, we would be able to ignore this change because it is just so small. In our second example, we have an unlabeled beaker. So a student has labeled a beaker 0.2 mole per liter acid, but has not included the name or formula of the acid. The pH of the solution is found to be 1.470. What should the beaker be labeled? So we are going to start by writing an ICE table for our generic acid. So HA plus water will be in equilibrium with A minus plus hydronium. And we're going to fill in what we can from the question. So we know that our acid is 0.200 moles per liter. So that's the initial concentration of our acid. And we know that we can cross out the entire column for water. As always, we never have any conjugate base or hydronium at the beginning of the reaction. Now, We don't know the Ka, we're solving for it, but we can solve for the hydronium ion concentration at equilibrium. This is because we have pH. So our hydronium ion concentration is going to equal 10 to the minus pH. So 10 to the negative 1.470. That's going to equal 3.39, so 3 sig digs, keeping our 3 sig digs, times 10 to the negative 2 moles per liter. So we can fill that into our table. We know that we have 0.0339 as the equilibrium concentration of hydronium, and therefore also of our conjugate base. So we know then that the change for our products is positive 0.339 moles per liter, and the change for our reactant must be negative 0.0339 moles per liter. So we can figure out our equilibrium concentration of our acid by adding down that column, and we're going to get 0.166 moles per liter. We can take these values that we have at equilibrium and we can solve for the Ka. So our Ka value is going to be our conjugate base times hydronium divided by our acid, and all of these will be our equilibrium concentrations. So we will have 0.0339 moles per liter squared on the top and 0.166 moles per liter on the bottom. That gives us an equilibrium a Ka value of 6.92 times 10 to the negative 3. We can then refer to our acid-base chart to see what this is going to be. And if we look, we see 6.9 times 10 to the negative 3 is the Ka value for phosphoric acid.